Good day, I'm Dr. T and welcome to my office. Today I'd like to talk about reaction rate. Chemical reactions don't take place instantaneously. It does take time for all the molecules to collide and become from reactants and turn into products. So let's look at a couple of things that are going to affect the reaction rate. The very basic one is simply what reaction are you doing? The molecules or atoms involved in that reaction are going to have to collide. Now, some reactions, they can collide in any old configuration and boom, the reaction happens. In others, they have to collide in a very specific configuration, and as such, most collisions aren't actually going to do anything. So those reactions are going to be inherently slower. Additionally, when they do collide, even if they're in the right configuration, they need to collide with enough force to actually get the electrons to move around and to cause a chemical reaction. That's what we refer to as the activation energy. So the more activation energy you have, the harder they have to collide, and the fewer of them that are going to be going fast enough in order to actually get that reaction to go. Therefore, the slower your reaction. Now, as far as configuration of the particular reaction, there's not a lot you can do with that. But that activation energy, that does give you a couple options if you want to speed up or slow down a reaction. If you want to speed it up, you can add a catalyst. Catalysts are chemicals that are going to be involved in a reaction but aren't used up in the reaction. And the way they work is they actually fundamentally change the nature of the reaction so that it now has a lower activation energy. I sometimes like to think of chemistry as like bad dating advice, and so a catalyst is kind of like a dating website. It fundamentally changes the way you meet someone, but it does make it easier to meet someone. The alternative, or in conjunction with a catalyst, if you wish to speed up a reaction, is simply to increase the temperature. The higher the temperature, the faster the atoms and molecules are vibrating and moving around, and therefore the more of them will be traveling fast enough when they collide to get a reaction to go. Conversely, if you want to slow down a reaction, then you would simply lower the temperature. That's how refrigerators work. By keeping your food cold, the reactions that lead to food spoilage are slowed down, and therefore your food stays good for longer. Now, other factors, of course, are going to involve anything that affects, those collisions. And, well, how much reactant you have does make a big difference. Not really total quantity, but concentration. So back to the analogy of, LA versus Wyoming. LA is going to have more car wrecks because there's more cars there. And a car wreck is kind of like a reaction. So two things have to collide. If there's no atoms easily available to bump into, then you get very, very few collisions because you're just not that dense of a population. Whereas if you increase the concentration a lot, you can get a reaction to go really, really quickly. This has a couple of interesting implications. For starters, if you have any friends, family, or if yourself are on oxygen, you'll notice that there is usually a concern about fire. And quite often folks who are on oxygen therapy will have signs basically saying no smoking in this house because the amount of oxygen in the house, the concentration of oxygen in the air in the house is a little bit higher because of their oxygen therapy. Now, because that's higher, then chemical reactions like fire that involve oxygen will take place faster. Therefore, the house can burn down very, very quickly and a fire can rage out of control before one has an attempt to stop it. And even things that normally wouldn't burn meaningfully could burn quite well in a high oxygen environment. Additionally, this is why we have to be careful with certain concentrated reagents. In dilute amounts, the reactions that they cause are slow enough that we don't really have to worry about them. But at higher concentrations, well, you have to worry about it. When it comes to reactions that involve not mixtures, but reactions on the boundary between two substances, such as when, say, a solid burns, etc., then those are going to be affected by the amount of boundary, the amount of surface area between those. This is why flour is actually a fairly significant fire hazard if it gets all foofed up. When it's packed in, there's not a lot of boundaries, and most of the flour isn't really exposed to the air, so if you tried to put a light to it, it would just kind of char. But if flour is poofed up, because it's a fine powder, there's lots and lots of surface area on that, it can actually explode. And there are several cases of flour mills literally exploding when a spark ignited the flour in the mill. And by the way, I'm talking about the stuff you bake bread with, not anything fancy. The same would go if you're dealing with, say, a liquid that needs to evaporate. fine aerosols will definitely cause a faster reaction than large clumps. And you'll see this with, say, things like fuel injectors. So yeah, that's a brief look at chemical reactions and their rates. Obviously, different things have different rates, and there's lots of things you can do to start manipulating those rates to get it to the way you want to do. So with that said, have a wonderful day.